Okay. So here is an arrangement for the production of X-rays, and the arrangement is known as Bragg spectrometer. As you can see, it has a filament, right, and the voltage is applied. High voltage is applied here at the filament, and when these filaments get heated up, electrons are emitted from the filament. The process involved is thermionic emission, right? And then here is the tungsten target where this electrons strikes, right? When that electron strikes or collides with this target, right, then the energy is released, and that energy is released in the form of photon with a particular frequency, and that emission is called as X-ray emission, right? So what's happening here, then these X-rays are collimated by parallel plates, and then they are incident on the crystal, lithium fluoride, quartz or diamond, right? Collimated means to make them parallel, right, to make them parallel, and then they fall or incident on the crystal like lithium fluoride, quartz or diamond. Okay. So, as the interatomic distance is of the same order as the wavelength of X-ray, diffraction is produced and they are detected by counters or photographic plates. So, thereafter, when they strike the crystal of lithium fluoride or diamond or quartz, of course they get scattered, right? And they get scattered, and they have a specific wavelength which is of the order same as the interatomic distance, right? And after scattering they are detected by the detectors. Okay. So this is an arrangement where the X-rays are produced. This is called as Coolidge tube. Okay. Now again you can see the arrangement. Here there is filament, right? Filament where the necessary voltage is applied. Okay. So when the high voltage is applied, these filaments get heated up, right? Now this is the envelope, and here there is a tungsten target, as you can see. When the filaments get heated up, electrons are emitted, right, from those filaments, and they strike the target, right, tungsten target. After collision with the target, right, they are accelerating towards the target, so they possess energy. So that energy can be utilized in two ways, whether it is converted into photon or it is lost in the form of heat energy. So two possibilities are there, but when it is converted into photon, the useful X-rays are produced of required frequency or the wavelength, I can say. Now let us see some of the properties of X-rays. Here's the first property, that it has very short wavelength of the order 0.1 angstrom to 1 angstrom, and of course we call it as electromagnetic radiation, right? So as we have just seen that with presence of particular potential, high potential I must say, right, that electrons get accelerated towards the tungsten target, right? And when they hit the target, and after hitting, X-rays are emitted, right? So let me call that the energy of emitted in the form of photon is given by h nu, right? And if I say that the total energy which was gained by the electron is converted into h nu, so that energy will be E into V, right? So this is the high voltage and high energy, and for high voltage and high energy you can say that the lambda is short, right, because nu is equal to C by lambda. So for high voltage and high energy, lambda is short. So we say that X-rays have short wavelength. Then These are produced when metal anode is bombarded by very high energy electrons that we have just seen. Very high energy electrons get collide with the tungsten, right? Then yes, X-rays are not affected by electric and magnetic field, as we have seen that X-rays are nothing but the photon of specific wavelength and frequency. So obviously these are not affected by any electric and magnetic field. That means electric and magnetic fields are not able to apply any kind of force on X-rays. Yes, and they cause photoelectric emission. Yes, they are capable enough to cause the photoelectric emission. That means when they are incident on the metal plate, then the electrons can come out from the metal plate, and this is called as photoelectric emission. So X-rays are capable enough to perform the photoelectric emission, that we can see. Okay, so the characteristics equation of X-ray is given by, I have just told you that, right? If the V potential is applied and electrons are accelerated with the application of this potential, of course the energy will be EV, right? And when I say that this energy is converted into two types, whether it is lost in the form of heat or it is converted into H nu. If I assume that the whole energy is converted into H nu only, then I can say that this equation is true. So E into V is equal to H nu, nu m, or nu is the same thing, is the frequency of X-ray radiation, and further you can say that this becomes C by lambda, right? Because we know that frequency is C by lambda. Yes, these are the terms which are already told to you. Yeah. Intensity of X-rays depends on number of electrons hitting the target. Okay. Now here you can see the graph, right? The graph of intensity versus wavelength, and here you can see there are three different characteristics. Here there is this characteristic, you can see this is known as continuous spectrum. I'll let you know what is the meaning. And then these are the characteristics where it is written as K beta and K alpha, and you can see in K alpha intensity is higher, and comparatively in K beta intensity is lower. Okay, so this intensity depends on number of electrons hitting the target. Again, there is the difference between continuous spectrum and characteristic spectrum as well. I will let you know what is that difference. Now let us see what is the difference between continuous spectrum and characteristic spectrum. Actually there are number of characteristic spectrum, but here we are mentioning only two. One is K alpha and other is K beta. Okay, so when I say electron jump from n is equal to level 2 to level 1, right, then the characteristic X-ray will be in the series K alpha. Okay, and when electron jumps from level 3, which level I am talking about? Energy level, right? Level 3 equal to level 1, then that will be K beta. Now there are other also characteristic spectrum, but let's not discuss that here. Then what about continuous spectrum? Continuous spectrum includes all possible wavelengths. Like from lower to higher limit. Right. So this is all about continuous and characteristic spectrum. What about cutoff wavelength or the minimum wavelength? Okay, let us calculate that. per volt, right? Per volt, what is the minimum wavelength produced in X-rays? So again, let me use that equation, characteristic equation. EV is equal to h nu, which is equal to hc by lambda, right? So I need to calculate lambda. So lambda is equal to hc by E 1 upon V. Okay, per volt we need to see. So when I put all the values here, like for H, when I put 6.63 into 10 to the power minus 34, for C I put 3 into 10 to the power 8, and for E I put 1.6 into 10 to the power minus 19, right? All of these values give me the minimum or cutoff wavelength as this 12400 angstrom, but per volt, right? Per volt I am getting this cutoff wavelength. So this is all about the calculation only, nothing else. Okay. So like I have just told you that characteristic spectrum is produced due to transition of electron from higher to lower energy levels, and we have also specified K alpha and K beta series. So here the frequency, right, frequency of X-rays depends upon this particular equation where A and B are the constant and Z is atomic number of the target, atomic number of target. That means if I am using tungsten, then Z is the atomic number of tungsten. So it depends at what target that electrons are getting collided, and after collision what characteristic X-ray will be formed, right? So this is the dependency. When I take root here, you can see the frequency, right? Root frequency is equal to root A into Z by B. If I plot a graph between this root of frequency nu and Z, right, I'll get a straight line. As you can see, I'm getting the equation in the form of y is equal to mx plus c, right. So here B is a shielding factor and it has different value for different series, and again A is constant over here. Now there are certain formulas of which we should make a note, right? So out of which first is Bragg's law. Bragg's law is given by 2d sin theta is equal to n lambda. Lambda is a wavelength, right, which is emitted, okay, in the X-rays we can say, and d is the interatomic space, and theta is the scattering angle. Yes. And we can say that this theta is the angle which is responsible for maximum intensity. Then when the electron is revolving in the orbit around the nucleus, its binding energy is given by negative of total mechanical energy. Binding energy is responsible for binding the electron with the nucleus, and we already know that this binding energy is negative of total mechanical energy. Actually we are making a note of this formulas just to make us aware, so that we can solve the numericals if we need to have this information with us. Velocity of electron in nth orbit of hydrogen atom. How do we calculate this? So here is the formula. Here you can see it is given by c by 137 n, where c is speed of light, right, and n is the orbit number. Again for X-rays, the wavelength is given by, as you can see, this r into z minus b whole square 1 upon n1 square minus 1 upon n2 square, where we know that this r is the red box constant, z is atomic number, minus b is again the factor which is dependent on which characteristic you are getting, and n1 is lower energy level and n2 is higher energy level. Series limit of series means minimum wavelength of that series. Okay, this is also one of the term, series limit, which shows you the minimum wavelength of that series. Then production of continuous spectrum. How the continuous spectrum is produced in the X-rays? The accelerated electrons are suddenly stopped by the target. As we have seen that when the electrons are emitted by the filaments, they are stopped by the target when they collide, right? Then after that, wherever a charged particle is accelerated or decelerated, they emit the radiation. So this is called bremsed lung or braking radiation. This is the name of scientist. So after his name, we have given this name to that radiation, bremsed lung, right? Or the braking radiation, we call it as. So when the whole energy of electron is converted to radiation, one gets the maximum energy or minimum wavelength. Like we have seen, the whole energy of electron is electron volt, right? EV. And when this whole energy is converted into h nu, so this becomes hc by lambda, right? So for maximum energy, minimum wavelength is responsible, that we can say. So if V is the potential difference applied, it is converted to the kinetic energy of the electron, right? So yes, this is the expression, and this is the expression for lambda, we know that. Okay, how this expression came? This is kinetic energy, which is equal to hc by lambda. So lambda becomes hc by kinetic energy E, and this kinetic energy E is nothing but E into V.